Hi everyone. I have started this channel for fifth semester mechanical engineering students to help them with their subject dynamics of machinery. So I'll be discussing some topics which are relatively hard for students to understand on their own. So even with some of the classes, when we try to explain, it some of the things are distant, and through online classes, as it is the thing right now, most of the students find it a little bit hard to capture all the concepts, and even when they do the problems, they are having so many doubts. So through this channel, I intend to clear many of the doubts, so which I feel which is recurrent in most of the students, as I've seen through the years. So most of the students they have the same similar kind of doubts, that is over the years, as we see. So I'll try to cover those points a little bit more precise, in a little bit more precise way. And in this channel I'll be giving you some of the things that I've seen in the textbooks. When we refer some of the textbooks, three four textbooks, when we refer, we tend to feel that maybe some of the topics are contradicting each other, some such doubts which usually occurs in dynamics of machinery subject. So those things I'll try to cover, and within the confines of the video, how much we can cover in a topic, that we will see as it goes through. So the first topic that I'd like to discuss in dynamics of machinery is static force analysis. So let us see what all things we can study in static force analysis, and what are the common doubts that people have, and we'll solve maybe, if time permits, we'll solve one or two problems from the same topic. Okay, so let's see static force analysis. So in static force analysis, since it is a little bit lengthy when we do the problem, and since there are so much of drawings involved in this topic, most of the students find it a little bit hard. But I can assure you that once you get the concept, this is one of the easiest topics that you can easily score marks in. That is static force analysis, because the concept is the same, and then you don't have to think too much, and you can save your time, because the method is the same in all the questions, only the values will differ. So once you are used to the method and you know your fundamentals correctly, this topic will prove to be very easy for you. So let us start with our static force analysis. So first of all, let me tell you what a static force analysis is. So and where it is used, why it is used. So static force analysis is mainly done when when you have to analyze the forces in a body without considering the inertia forces and masses that are in the body. So when we consider the masses and the inertia forces caused because of those masses, that becomes dynamic force analysis. That will be our next chapter that we will be discussing. So in static force analysis, we are only considering the forces that are acting on the system and the reaction forces that are occurring inside the system, that is in between the links. What all reaction forces that are occurring. So these things constitute, when we are considering only these forces, then we can call it as static force analysis. Okay, so static force analysis can be done in both analytical way as well as your graphical method. So we will be covering graphical method in this channel, and I'll try to cover it as make it as simple as possible. So let us start static force analysis. So before going deeper into the problem and exactly solving the problem, before that let me just tell you some of the basic things or rules and sign conventions and namings of involved with static force analysis, because these things will make it easier for you when you are solving the problem. Okay, now the first thing I would like to cover is, now suppose you are taking a slider crank mechanism. So what is a slider crank mechanism? You have a crank and a connecting rod, slider, and it is acted upon by one force. Right, so this is my first link, which is my fixed link. This is my crank. This is my second link. Connecting rod is my third link, and slider is my fourth link. So I have 4 links in this mechanism. Right, now I have one applied force P, which is acting on this slider crank mechanism. Right, so when we get such a system or a mechanism and we are asked to solve it by static force analysis, what we have to do, what we need to understand first of all is the force is being acted upon this one, the slider, and the slider will move, and which will cause your crank to rotate, right? So your crank is going to rotate when the force is going to get applied from your crank is going to rotate towards in anti-clockwise direction. So now before we delve deeper into solving this one, first let us see one by one. Let us take the links one by one. Now in this problem you have 3 kinds of members. The first one is member with two forces being applied on the member, that is 2 force member we can call it. And the second one is a 3 force member. And third one is member with 2 forces and a torque. Okay, so there are 3 kinds of members existing in this mechanism. So the first one is 2 force member. So 2 force member, what is a 2 force member? Let us see. So in a two force member, which is the connecting rod over here. So if I take the connecting rod, as per rule, whenever on a mechanism, any mechanism, 2 forces on a link, any 2 forces are acting. So let me just mark this one. It's 1 force. So let this be F1 and let this be F2. So as per rule, the forces are equal and opposite to each other. So the forces are equal and opposite to each other, and they are collinear. Equal and opposite to each other, they are collinear, Okay, so these things we should keep in mind always whenever it is a two force member. So this thing will be taken for granted in all when we do throughout the problem. So this is a base rule that you have to remember throughout the problem. So in a two force member, you have two forces acting on a member. Those two forces are always collinear. Collinear means it is in one single line. So when it is, suppose this is the link 3, when two forces are acting, these two forces are equal in magnitude and they are opposite in direction and they are in the same line. Okay. Now the second one is a three force member. Now if I consider a three force member, then you have three forces acting. Which are F1, F2 and F3. So as per rule, these three forces will meet at one point. So these three forces will meet at one point and the resultant of these three forces will be 0. That means it will form a closed triangle, a closed polygon. Okay, so here the rule is all the three forces meet at one point and the resultant of these three forces are, resultant is 0. Okay, so resultant is 0 means the force polygon, if we draw the polygon with these three forces, then we will get a closed polygon. Okay, so that is the three force member. Now let us see two forces and a torque. That is the last one that we are left with, right? So two forces and a torque. That is the third condition. Which is your crank over here. In this case, the crank over here, that is the second link, is having a torque T as well as two forces acting over here. So one force being like this, F1, and F2. Let us just take random forces. I am not naming the forces as per the sign convention as of now. We'll study that in the next part. So here in this one, two forces and a torque, when it is acting on one single link, the rule is these two forces are equal in magnitude, and opposite in direction, and they constitute a couple. Together they form a couple. Okay, so here this couple is given by the formula. This any one force you take F1 into H. So here T is equal to F1 into H, that is force into perpendicular distance. So couple is nothing but force into perpendicular distance. So I am taking F1 into H, where H is the perpendicular distance between these two forces, perpendicular distance. So if I take the perpendicular distance, this should be perpendicular, and this distance, if I take, that is my h value. So most of the students, when they have some confusion when they are taking this h value sometimes, because they usually tend to mistake how to measure this h. Now it is nothing. When you have to measure the distance between two parallel lines, what do you do? You draw a perpendicular line to these two parallel lines and measure that perpendicular line's length. So that is what we are doing. These two parallel lines are there. They are equal in magnitude, opposite in direction, and parallel to each other. Parallel to each other. And they form a couple. So this is the first basic fundamentals that we have to remember. Now let us see our sign convention and how to name the forces. That is the second thing that we are going to discuss. So I hope you have noted this down. So let us see. Now, if I take now let us first see the how to name the forces. So if I take my second link, which is my crank over here, so this is my second link on which I have a torque T as well as forces which are being acted upon. So here the force is getting acted upon from 3 onto 2 as well as from 1 onto 2. So here the forces, when I write, I have to write it as F32 and F12. So 2 always comes second because that is the link is 2. So onto that link the forces are being acted upon. So you have to name it as F32 and F12. So from 1, which is my fixed link, the force is being acted upon onto link 2 as well as from 3 onto link 2. So now let us see our third link. This is my connecting rod. So on the connecting rod I have two forces. So as I told you, it is a two force member in this case. So here I have F23 and this one will be F43. Okay, so here the force is being acted upon from 4 onto 3 as well as from 2 onto 3. So 3 comes second always. Okay, now if I take my fourth link, which is the slider crank, so in the case of slider, I have a known force P acting over here, right? And then I have F43. When it comes over here, it becomes F34 and I also have an F14. F14. Now this is a link with three forces acting upon it. So the member with three known forces, three forces acting upon it. So here this is F34, that is from 3 onto 4, F14, that is from the fixed link onto 4, and P. So here that is how we name. Now regarding the sign convention, your F34 is equal to minus of F43. Okay, F34 is equal and opposite to F43. So if I have to put the direction of this one as like this, then F43's direction will be in the opposite direction, but these two are parallel to each other. Similarly, F23 also will be opposite to F43. Why? Because it is a two force member, and in a two force member, what did we discuss a little while earlier? In a two force member, both the forces are collinear, they are equal in magnitude and opposite in direction. So here I have F43 is equal to, that is minus of F43 is equal to F23. Right. Now, next one, here I have F32. Now this F32 is again, F23 is equal to minus of F32. This minus sign is always indicating your direction, opposite direction. Right. Yes, so that is it regarding your sign convention. So now let us do a static force analysis for one force when it is getting acted upon your slider crank mechanism. So one known force in a slider crank mechanism, we will see how that method is, and then later we will go on to 4-bar mechanism, one known force, and then we will go on to two known forces getting applied on both slider crank and a 4-bar mechanism. Let us see how much we can cover in one single video. I wanted to keep this static force analysis as one single video, but let us see how it works out, so that in one single video concisely, if you watch it fully, you will understand the whole concept of static force analysis. Right, so I have already drawn these figures, so let us go with the same thing. Now over here, it is static force analysis of a slider crank with one known force. So let us see. Now we have one known force getting applied over here, that is P, on my slider crank mechanism. I have a slider, connecting rod and a crank. Now first step that we have to do in whilst doing the static force analysis is draw the space diagram. Now this is our space diagram or configuration diagram. So different people call it in different names. So you can call it as space diagram or configuration diagram. So first thing is we are drawing this as per a scale. So in the question, measurements will be given to you. So you draw it as per scale. Now this is a very, very important step, that is drawing it as per a scale. Now some students usually have this doubt with scale conversion. Scale conversion is it is a very simple thing to understand. That is, I have a huge length, maybe 2 meters or 3 meters length, but I cannot show it in my figure, right? So I am showing maybe 3 meters of length as 3 centimeters. So the unit conversion that we take, that is what we mean by scale. What scale we are going to take over here, right? In simple words. So here I am drawing my configuration diagram. That is, I'll go step by step. So first step 1 is draw the configuration diagram as per any suitable scale. Right, so I'm not writing that heading. So draw the configuration diagram with a suitable scale. Next step is to draw your free body diagrams. Now, free body diagram means you are taking links, each link separately, and you are marking the forces that are being acted upon on those links. So you are only concerned with the forces that are being acted upon those links. So here, when we are drawing the free body diagrams, what we come to know is we are clear with which all forces are acting upon on each link. That is what we tend to achieve from free body diagram. So these are the free body. This is the free body diagram for second link. This is third link, and this is fourth link. Right. So on the second link, I have two forces and a torque. Now, let us come to our problem at hand. So here, how do we come to know the F34s and F43s direction? Now we actually don't know the direction of any of these forces other than my force P. So I have one known force being acted upon P. That is the only known force that we know. So first, when we draw the free body diagram of my connecting rod 3, I know that it is a two force member, and the two forces are equal and opposite to each other, and they are collinear, right? So I know that F23 and F43 are equal and opposite, but I don't know its direction yet. I just know its line of action. So I just know that these two forces are going to act in this line of action, but I don't know its magnitude as well as direction. So that we have to find out by drawing the force polygon of this link. That is my link number 4. Because the only known force that we have is P, and that is being acted upon over here. Now F14, now if you see this green, the force that I have marked in green, it is F14. Now whenever a slider is sliding with respect to something, with respect to your fixed link, the reaction force is always perpendicular to it. So your F14 is always going to be acting perpendicular to the slider. That is the movement of slider wherever it is acting perpendicular to that line of stroke. You have your reaction force acting. Right. So this is my maybe first YouTube video. So pardon some mistakes. Okay. So in between, I'm not used to recording myself. Yes. So as we move forward, let us see by solving. Let us start by solving the force polygon. First force polygon for my link 4. Right. So this is my free body diagram. Now as my step 3, I'm going to do I'm recording this at night after everyone has slept in my home. So I'm also a little bit sleepy. You can see my face a little bit sleepy. So here the step 3 is I'm going to draw the force polygon for my link 4. Right. So let us take, now here we have to draw it as per a scale. Right. So we are going to draw the force polygon. Why are we drawing the force polygon? We are drawing the force polygon to find out the direction of this F34 as well as the magnitude of this F34 and F14. So this is my objective by drawing the force polygon. So for drawing the force polygon, I have to take a scale. Now here in this case, in first case when we took the scale, it was a length conversion, right? So meters we are converting into centimeters, that both are length. But in this case, we are taking force and we are drawing it as a line. So the force we are taking and we are converting it into we are assuming it to be a length. Right, so this scale conversion is different from this scale conversion. Okay, so because most of the times students, when you have a number of scale conversions in the same problem, some students tend to get confused. They will take the same scale and all. That is not needed. Let us see. So here, suppose P is given as maybe some, let us take a random value, 2000 Newton or something. So P is known to us. In the question, it will be given to us, or when we are solving question, it will be given to us because that is the only one known force that we have. So P is 2000 Newton. So I am taking P as maybe 10 centimeters or 100 mm. So here we are taking 100 mm is equivalent to 2000 Newton. Right, 100 mm is equivalent to 2000 Newton. So here I can write as 1 mm is equivalent to 20 Newton. So when we are writing the scale, you always have to write the units along with it. So here I am writing 1 mm is equivalent to 20 Newton. Right. So let us draw the force polygon now. I have P acting over here, and so P I am drawing a 100 mm line, right? Because that is the 2000 Newton. So, and I know its direction also. So parallel to this, I am drawing over here P of 10 centimeter or 100 mm I have drawn. Now, what else do I know? I know that this is F14 and this is F34. These two line of actions I know. So what I'll do, I'll draw the F14 from here and F34. These two I have to draw. So F34 I'm going to take from here and I draw over here, and F14 I take from here and I draw over here. So parallel to this F34 I'm drawing So parallel to this, I'm drawing over here F3, 4, and this is my P. Now what am I left with? I have F14. So F14 I'm going to draw from the other side of P, parallel to this. the direction. I don't know the direction of any of these forces, right? So this is F14. So F14 is going to act in this direction and F34 is going to act in this direction. Now how did I come to know? What I have to do is I have to just follow in the same flow in which P is acting. So here P is acting in this direction, so F14 in this, and F34 will be acting in the same flow. So I have to mark F34 also in the same flow. So just from this one force polygon, what am I getting? I am getting the measurement of F34. So what I do is I can measure this value of F34, that is the length. Length I am measuring from here, and I am converting it back into this scale. So here F34 I am taking and I am converting it back into the scale. So I'll get a definite value. So maybe this is supposed to be right angle, so this is hypotenuse, and so this will be bigger. So you will get somewhere around 2300 or 2400 Newton. So here this F34 is going to be measured from here, this distance, the length, and I'm converting it back into Newton. So I'll get the value of F34 and the direction of F34 I obtained from here. So both I'm getting same as F14 also. F14's value, that is magnitude and direction, I obtained. So from here, what is it that my whole problem is actually solved, because if I'm marking over here F34 is acting in this direction. So if F34 is acting in this direction, then F34 is equal to minus of F43. So which means that F43 is acting in the opposite direction to it. So if F43 is acting in this direction, then as per my two force member assumption, my F23 is acting in the opposite direction to it. So F23 is equal to F43. So here minus of F43 is equal to F23. Similarly, this F23 is equal to minus of F32. So here F32 is acting in the opposite direction to F23 but parallel to it, and F12 will also be acting in the opposite direction to F32. So here these two forces are acting in the opposite direction to each other, but they are parallel to each other. So what I do is I have to measure the perpendicular distance over here between these two forces, which is H. Okay, so this is a two force and a torque member. So here what I did, I found out the value of F34, right? F34. I got the value from here, measured from here, I got the value after scale conversion. So after I found out that, literally my whole problem is solved then and there. Right, so this F34 is equal to minus F43, minus F43 is equal to F23, F23 is equal to minus F32. So literally the whole problem got solved then and there itself. So here F34's value I got. So at the end, what am I getting over here? Here I need to find out. Now the question that will be asked to you in this static force analysis problems is find out the torque required, input torque required to keep the system in equilibrium. So what is happening over here is P is acting from this side. So automatically, based on your common sense, what is happening over here? Your crank is going to rotate towards this side, right? In anti-clockwise direction. So if you need to keep the system in equilibrium, what you need to do, you need to apply a force, a torque from here, that is in clockwise direction. So then only your system will be in equilibrium. So what I have to find out is, I have to find out the input torque that is required to keep the system in equilibrium. So for that, my input torque will always be opposite to the torque that I'm finding out over here, right? So this one is in the anti-clockwise direction, so I'm going to take it as, negative. So here T is equal to minus of F32 into H. So I'll be getting a negative value over here, right? Now my input torque is supposed to be opposite to this T. So if I name input torque as T2, so T2 is equal to minus of T, right? But here I already had a minus, so minus minus will become plus. So T2 is always opposite to that of my torque. It is my input torque is always going to be opposite to the torque that is generated in my crank. So here my static force analysis of a slider crank with one known force is done. So you can put in any values, over here 2000 or 4000 or 6000, whatever value, but the method is the same, and correspondingly your answer will vary, but the method is always the same. So that is why I told at first that it is so simple. Now next we will see slider crank with two known force.